I'm going to talk about a library I've been working on. I haven't pushed yet. I'll come up with some excuses later. The code is mostly written, but given it's a crypto framework, I want the testing to be completed before I actually push it, in case anyone does anything silly enough to use it. Okay, so
this is the good crypto, not the bad crypto, right?
This is proper crypto, not new kids, not the young kids crypto. It's like it's got nothing to do with Ponzi schemes or other rubbish, modern rubbish. Well, it is modern, but it's not rubbish. So what Vixen is an implementation of something called the Noise Protocol Framework. And you can go online and see what that is. It is a framework. It isn't itself like a network protocol. It doesn't say how bits should be laid out on the network. As the bullet points show, it combines a number of things. Cryptographic primitives, we'll cover those very briefly. Handshake patterns. When you combine those, you do get a protocol. We're still not sort of network specific. It doesn't care whether or not it's TCP or UDP. It actually has nothing to say about how things actually get shared between parties. But the goal of the framework is to execute a handshake that will establish a secure channel between two parties. So who knows what Diffie-Hellman key agreement is? Ish.
Me.
Rough idea. Public key cryptography, RSA. Okay, RSA is kind of like an instance of the theory of Diffie-Hellman key agreement. The idea is that there is an algorithm that allows two parties to generate a key pair. Each party has a private key and a public key. They share with the other party their public key. Both parties combine their private key and their public key to produce a shared secret that was not transmitted. And then you can use that shared secret to seed a symmetric cryptographic algorithm. The noise framework, really the whole foundation of it is Diffie-Hellman key agreement, and the different protocols combine various rounds of Diffie-Hellman key agreement in different ways, and we'll sort of briefly look at those. Okay, so what are the crypto primitives that it actually uses? This is the headline stuff. So I'll go through the types. So there are basically three types of primitives that it uses: hashing, which you're probably familiar with, a symmetric cipher, an AEAD symmetric cipher specifically, which allows you to authenticate that what was sent has not been tampered with. So it isn't just like AES or even like RC4 or something, or even CHAR20. It isn't just like send some bits to you and then you decode them and then you just sort of take it on trust. You can verify whether or not the bits have decoded without tampering. So it's symmetric cipher plus that authentication. And then the other primitives it uses are specifically elliptic curve Diffie-Hellman. So there are a number of ways of doing Diffie-Hellman. Most people are familiar with like RSA, which is often what people get by default when they use SSH keys. Elliptic curves are a way of an algorithmic way of coming to the same conclusion, to coming to a shared secret. They're generally more efficient. They're smaller keys. If you ever tell SSH to generate you an ECDH key, it's much smaller than the RSA keys. They're a bit easier to manipulate. And then the thing that's kind of cool about noise is that it actually prescribes exactly what instances of these protocols you can use. And there aren't many, and there's a reason for that, and that's mostly to reduce complexity and to make good choices. So for hashing, either Blake2 or SHA-256. For AEAD, there's an algorithm called CHAR-20 Poly 1305, or ASGCM. For what it's worth, the authors of the protocol framework recommend CHAR-20, but for most uses they're equally good. And then for the elliptic curves, there's basically two curves you can choose from. You don't really need to know the details, but these are common curves. And the other cool thing about these things is all these primitives are available in essentially Erlang's crypto framework. It's like first class choices. Okay, so every noise protocol, the purpose of the noise protocol framework is really to establish a secure channel. And to do that, it has to be a handshake. It's a sequence, sometimes only one, sometimes more, of Diffie-Hellman key agreements. Sometimes that always involves some form of like exchange of the public keys between the two parties. And then there's this operation we talk about where we combine my public key with my private key with your public key, and that produces like a big number. It produces the same big number for both parties, and that number itself is then further sort of hashed into the shared secret. And in fact, every round of the noise protocol takes the output of its Diffie-Hellman key agreements and hashes them into the shared secret, and uses those to ensure that both parties at every step of the framework agree on where they are. In the handshake, one party plays the role of the initiator and the other the responder. That's always true. We'll see in a minute. There's a way in which I can sort of demonstrate that. The initiator starts the protocol. The responder is sort of waiting, typically maybe a server. So the initiator would be some sort of client and the responder would be a server. The initiator starts the protocol, but both parties have their roles to play in executing the various handshakes. And then ultimately at the end of it, when a handshake completes, regardless of which handshake it is, you actually end up with this shared secret that's sort of rotated, enumerated through various values until handshake completes on both sides. Then what actually happens is it splits and rehashes that key. So you end up with two keys, one for an outbound channel and one for an inbound channel. So in theory, even if someone could crack one of those channels, they'd have to do exactly the same work all over again for the outbound channel. There are various sorts of keys involved in the protocol. We mostly won't cover pre-shared keys. Suffice to say, they exist, they sort of live outside the protocol. Like I coded something up and I hard-coded a pre-shared symmetric key into it and the server. And that sometimes you do that because it allows you to bootstrap. Even your first message is undergone some form of encryption. Without something like that, then your first message is always in the clear. Maybe you don't want that. All handshakes involve ephemeral keys. They're generated at runtime. They're good for that handshake only. So they only influence exactly the keys that result for that session. They provide forward secrecy. So they mean that if messages get cracked now, they can't be cracked in the future. Most handshakes also involve static keys. That means keys that we kind of agreed were going to be like, this is the key for the server, this is the key for the client. We agreed those up front. We probably shared them out of bands. Maybe we didn't. They provide, essentially they're there to provide some form of authentication. And I'll explain that in a minute. Okay, so the magic of noise is that it has this kind of DSL for describing a handshake. And you can go and read the paper on the noise website, which discusses all of these things and exactly what the steps mean. I've got two examples here. The names, these sort of two, the names can get a bit more complicated than that, but those names are basically, they've got kind of a nomenclature for the names, which is N means no one has like prior knowledge of a static key. And in this case, NN means neither party has prior knowledge of a static key. And in this case, in fact, that top protocol, NN, which is basically the simplest noise protocol handshake you can have, is essentially Diffie-Hellman key agreement. And so I'll just briefly talk through what that means. So it looks like these are messages because of the arrows, make it think like they're messages. But really what they're describing is a state machine and the steps both parties should take through this state machine in order to arrive at the secret key. So if you look at that sort of top line, there's this sort of right arrow and then the E. What that means is the initiator generates an ephemeral key pair and sends that public key to the responder. And before we move to their second line, the responder also has to process that top line. And for the responder, that E means take that key, that public key, and store it. And then, actually, I've actually got a bug in here. One of those E's on the second line should be a double E. What that means is we combine the two ephemeral keys. I generate the responder in the second step, then generates an ephemeral key. It combines it with the one it received from the initiator. Now it's complete. It now has a shared secret, and it transmits that public key to the initiator, and the initiator then does the same operation. So now both parties have arrived at a secure channel. It's very simple. That is essentially, that describes Diffie-Hellman key agreement to all intents and purposes. It doesn't say how the bits got over the wire, but it does describe the key agreement protocol. Now these handshakes have different properties. The thing about the top, it's very simple. Sure, we've got a secure channel, but we have no idea if we're talking to the person that we think we're talking to. There's nothing in there that authenticates the either peer. It's completely unauthenticated. So yes, it's encrypted, but who knows who I'm talking to? So anybody could get in the middle between me and the server and issue keys and read all my messages. It exists. It's simple. The second one is a different one. IK. So I means what does I mean? I think I means there is no key to. I means the secret key. The static key is sent, and K means the static key is known. K stands for known, effectively. And you'll see that there's an ellipsis in this protocol description. That means that what sits above the ellipsis is what happens before the actual computer program started running. Okay, so it's like a preamble. So what that means is somehow, we don't really care how, the responder sent its static public key, that's what the S means, it sent its static public key to the initiator. And then the protocol actually starts with the initiator sending an ephemeral key, combining its ephemeral key with the static key that it has, then sending its static key, and then combining ephemeral and static keys. And then essentially the responder does the reverse, and then it sends an ephemeral key, and both it sends an ephemeral key and combines static and ephemeral keys. So it's a much more complicated handshake. We still arrive at the same shared secret. And there was some authentication going on. So the server believes that the client trusts that the server is who they say they are. Because the client started with the server's public key and was able to continue the protocol. There are loads of these. There are absolutely tons of different ways you can combine them. The interesting thing is if you go to the noise protocol, they will actually tell you the various properties of the algorithms at each of the steps, like what material is secure at each step of the handshake. So If you do ever need to use something like this and step outside sort of TLS, then you can go and review the kind of properties that each of the handshakes have. And like I say, there are lots, and also there are lots of, I call them sort of, there are lots of features that you can add to them. So you can combine these with things like pre-shared keys at various stages in the protocol for the properties you desire. The protocols have names. These are effectively instantiations of the framework. There's an example of, like, you know, the top one says combine this particular Diffie-Hellman key agreement algorithm with this particular symmetric cipher with this particular hashing algorithm and use the NN handshake. And there's, you know, there's a couple of examples there. And so they sort of, they're like the instantiate. Once you have that thing, you can actually start talking to someone. Oh, interestingly, just to go back, IK, that's WireGuard. If any of you know heard of the WireGuard thing. So Tailscale, who's heard of Tailscale? Heard of Tailscale, WireGuard. WireGuard's the thing. Actually, WireGuard actually uses an extra cryptographic primitive that isn't in the noise protocol, but WireGuard is basically VPNs for mortals. Okay, so Vixen. So Vixen is basically an implementation of the protocol framework, and it's got a pretty simple API. I'll show you an example in a minute. You can construct with new, you can construct an instance of the protocol, and then essentially you advance the protocol by calling sort of read and write. So if you're the initiator, you're going to construct the protocol, and then you're going to call write to start generating messages. Now, again, just like the framework, Vixen actually doesn't really give a shit whether or not you're sending stuff over carrier pigeon or the network or whatever. It generates, you put input in, you get input out. How you deliver that to the recipient is up to you. The thing is that though, but what it does do is it implements what are called the processing rules of the noise framework. So it can take any of those handshake frameworks and execute them. So you don't sort of pick, you can literally hand it the thing. I might show you, let me just pull the screen over a bit here. I'll give you an example. Okay, this is Erlang, so it's probably going to be terrible, but I'll make it bigger. Let me bring this over. Okay, so there's an example. There's the, if you execute the framework and you ask for NN, that's what gets returned to the state machine, and the state machine actually executes those steps, depending on whether you're the initiator or responder. Executes the steps. And then we've got like XX, which is one we didn't discuss, and like KK, where we did. Actually, we discussed something like KK. So KK is a classic one where both parties have actually already exchanged static public keys, and then we start an ephemeral key exchange on the tap. That gives us authentication of both parties, but then gives us the forward secrecy that the ephemeral keys provide. And we'll look at the sort of API in a minute, but essentially I use exactly that. That's that data there on the right hand side is exactly what the state machine processes to execute the protocol. So you could literally write your own handshake mechanism and it would attempt to execute it. Okay, let's go back to size. Okay, why I wrote it in Erlang, you will come back to later. Okay, so this is what it looks like if you're roughly using it with some magic sprinkled for actual message exchange. Also, it's the Elixir meetup, so I had to alias the Erlang module in uppercase so everybody could read it. But I start by, I create a new instance of the protocol. I say I'm going to be the initiator. I tell it what handshake and which of the cryptographic primitives I want to use. There are more options than this. I lie them for time and effort. And then what happens is I say, okay, I'm the initiator. I just want to do a write. And that produces some output. That produces some output that needs to go to the server. This is all part of the handshake. Then I send that to the server and somehow I get a response back. We'll look at the responder in a minute. I take that input and I tell Vixen to read it. And because it returns OK and not continue, at that point, the handshake is established. And I can now actually, on the bottom line, I can actually use the result to encrypt over the outbound channel. So it's a very simple API, just basically instantiate, read and write. Sorry, go. Yeah.
Sorry, Ching, just a sec. Just so everyone online can hear.
I just wanted to quickly ask, is it always supposed to be a Vixen dot, or is it supposed to be colon sometimes?
Yeah, good spot. Yeah. Also, I discovered today that the README example on the Git definitely wouldn't compile. Most of it compiles, just not the bits that I wrote without any help. Okay, and there's the responder's view. So the responder in this case starts up, it knows what protocol it's going to talk. It then sits there waiting for a message, and it gets that first message that the initiator sent. It tells Vixen to read that message, and then tells Vixen, well, I need a response back. So, but at that point, it's done. It's read an ephemeral key. The next step in the state machine is for the responder to generate its own ephemeral key, in this case for using NN, is to generate its own ephemeral key, establish the crew agreement. So the responder is actually done at this point. However, it needs to send that message back to the initiator, and then it's essentially waiting on the channel to get data, and it can decrypt stuff over that channel. You can write, I mean, I'm doing this as part of the testing. You can write a generic handshake that just sits there going, do stuff, continue to write and continue to read until I hit OK, and it's established. In this case, I've sort of very explicitly, I know I'm using NN, so I'm going to send one message, I'm going to receive one message if I'm the initiator, and then I'm done. Or if I'm the responder, I'm going to receive one message and send one message, and then I'm done. So the code's written that way, but it's not difficult to write something where you could plug in the handshake sort of at runtime and have it just run until the handshake completes. Okay, so most of it's actually written. There's some stuff around pre-shared keys, which are in this kind of, they're not an addendum to the protocol by any means, but they're sort of, you can definitely run many algorithms without pre-shared keys. I need to add that. There's some stuff it does for you automatically. So for instance, if you give it, let's say we looked at KK before, and KK is a protocol whose DSL says both parties have to know the each other's static public key. That's what happens. The runtime will actually check that. So if you say, I want to use KK, one of your responsibilities, each party's responsibility, is to provide that static public key into the algorithm. And it will error if you don't. So it will say, you know, I don't have enough key material to sort of advance the protocol. In terms of like, you know, it's crypto, proper crypto, not kids crypto. What I'm working on, I've got all like the symmetric tests written, so the thing can talk to itself over a number of different handshakes and all combinations of cryptographic primitives. But the next thing, the thing I've started working on is there are some third-party third-party conformance tests that say if you do this at exactly this stage, your key material should look like this, and it's just a massive JSON file of super long hexadecimal numbers. So I'm working my way through that, but in principle, like once that's done, you should be able to talk to any of the whatever Python, C++, Rust. There are lots of implementations of the. There actually is an Erlang implementation of the noise framework. I don't like it, but there are other options available if you want them. And I want to get the basically full conformance up to at least what's covered in the actual noise protocol document. So that's about between 30, I don't know, it depends on, say, 60 different handshakes. So 60 handshakes plus pre-shared key, which can happen at any point in the exchange, times 4 hashing functions, times 2 different types of curves, times 2 different types of symmetric ciphers. So once that's up, I'll probably sort of push it to hex. So, and then, you know, an interesting thing about these is it's quite easy when you run, because the state machine is generic, it just runs off that little DSL that you saw. It's quite easy to get up to like 100% code coverage and still not have tested anywhere near the actual number of combinations that are actually in the wild. I think I'm currently running at, I don't know what it is, like 92% coverage, sometimes half for other things. I don't know, let's have a look, have I got it? See if we can find. Oh, it's down there, hang on, how do you can get that? Yeah, okay, so I don't know if you can see that. Vixen is where all the hard work is. Vixen Crypto is just a few calls that wrap the Erlang crypto library. Vixen DB is just the thing that stores all the different handshakes. I haven't filled it out by any means, but yeah, that's the current state of the library. It's been in a bit of a hiatus because of work commitments, unfortunately, but I hope to pick it up before I die. Okay, so there's some interesting design choices I made here. Every step of the noise protocol mutates some state. Right? Mutation is kind of at the heart of most cryptographic protocols, and if you read that, if you take the noise protocol author at his word, then any reuse of any of that state is considered like a cryptographic disaster. And so I considered an API where, like a functional API, where you give me the current state of the protocol, and then you give me the next message you want to send, and I give you a new message back, and then a new protocol state. And I just figured it's too easy to balls that up and just get it completely wrong, and maybe reuse the same state twice. So actually, the thing that you saw in the, I don't know if I can go back to this thing that's returned from new, I called it prop for protocol. It's just a reference, and it's a reference that sits inside the process dictionary. And every time you call write, the actual state behind that reference is updated and put back into the process dictionary. So it's not possible to accidentally use the wrong step of the cryptographic handshake. You can use the lower level libraries if you want. I wouldn't advise it. I'm not going to guarantee they won't change. This is the API that won't change. But that was like an interesting design choice, because it definitely, I didn't want to write this as a process-backed thing. Like, it's not my concern how you organize the actual messaging in your application. But without that, it would be quite trivial to write this as like a gen server, because you can just encapsulate all that in a PID. But I think that's like terribly wasteful to do that, essentially. And a reference in the process dictionary gives you essentially the same effect as a PID. And like, yeah, the thing you hang on to doesn't change, but the state it represents changes. But I just didn't want to use, there's a lot of binaries flying about as well. So like encapsulating it in a process I thought was probably not very performant. Okay, and why did I choose Erlang to do it in? I actually did start to write it in Elixir, which is fine. And then I realized that the actual API was going to be tiny. Like it is basically 3 API calls in one module. And I thought, well, why not just write it in Erlang? Like, and then that way everybody, it's like the base thing. You know, it's like writing things in C. Everybody gets to use it, right, at the end. So it's probably a bad idea. I liked it. I particularly liked, I did find it quite crufty, but just as a point of interest, I did find it quite crufty, and I found rebar quite crufty as well. Like it doesn't feel quite as nice as it Mix or whatever, but it's quite a bit faster. It, like the UI experience I thought was better. And also I found eUnit also crufty, but it was really nice to write tests, especially just the built-in way to generate tons of tests. And there's a lot of data generation in there. So yeah, it was like, I mean, I come from an Erlang background years ago, and you know, Elixir finally won me over. You know, a bit of lipstick goes a long way. It was kind of interesting to compare. I did find actually writing the code a bit trickier. I don't think the tooling isn't as good. Still, it hasn't caught up, even with like VS Code and what have you. It's not quite as good, and you just don't have as many tools to hand for code quality. But yeah, it was kind of interesting. I found Rebar it's more fluid experience in terms of just building and compiling. It was much faster. Not still, you know, it's not like Go or anything, but it's still better from that perspective. Yeah. Anyway, it's enough rambling at the end. Any questions? Oh yes, I've got to give you the obligatory, don't ever use this because it's crypto, and like you should never use it unless there's like an authorized cryptographer in the room. To be fair, most of this is, you know, if you pass the conformance tests, I think it's good to use. They're not random selections of cryptographic primitives. The whole thing's been sort of vetted a gazillion times. So if you pass the conformance test, I think you're good to go.
Who was the, yeah. No, it's all good to speak.
Oh, yeah. Hi. Thanks, Nick. What use cases would something like this be used in?
That's a really great question. So if you can get by with like TLS, you definitely should. Interestingly, TLS 1.3 has a number of things that are in noise, which are considered like best practice now. Things like the use of ephemeral keys to guarantee forward secrecy. So there are, and also you'll notice if you ever read the specs, how the specs evolved, TLS 1.3 just went, all these algorithms, they're gone. Like we're only going to pick a few known good ones. I mean, most of, you know, a lot of the world's still on TLS 1.2, but so they share a lot in common. If you don't want certificates, if you don't, you know, if you're happy to and send your clients out with public keys, static public keys, and they're public keys, so who cares? But yeah, if you don't want to do certificate management, if you're maybe you're doing maybe IoT stuff where they don't have TLS, it's unlikely nowadays, but any sort of custom framework, maybe you want client authentication without certificates. That might be a reasonable one. And one of the protocols we looked at there, KK, for instance, will do mutual authentication. Yeah, I wouldn't. If you have a library to hand that does TLS, and you can handle a certificate thing, then that's fine. I would use that.
Does anyone else here have any questions?
Well, actually, I was on holiday in Bateman's Bay, and my wife thought it was a terrible idea for me to sit coding. But I had great view, so we had hired this house, and I had this beautiful view of the sea at the house, and yeah, I did. I kind of passed the time of day. We get to my age, I don't want to go to the beach, so I just thought, yeah, I've got a beautiful view. I'll smash this out, um, and I'll give a talk about it. Um, yeah, it's did I mean did I have fun from like I quite like I did quite like going back to the minimalism of like writing in Erlang. Not so much like the tooling. I think if Erlang just had some more attention in the tooling, it would still be good. But the language is still, you know, it's much simpler, less expressive. Um, some people think that's a good thing. I think that I particularly miss macros. You know, the DSL would be like a perfect, you could make the DSL look much closer to how it's like written in the noise protocol framework document. And that was tempting, but I didn't want to like make, the other problem with that is like, oh, now I've made my implementation depending on macros and basically eliminated any Erlang user base. And I didn't see that there was a big advantage to that when the API itself was so minimal. Yeah, I'm always having fun coding. It's all fun. It beats working, right?